So next semester going to be online too. That's the plan. It's the plan. Uh, I mean, the virus is still, you know, I don't even think people in charge are even, like, at any level, are even pretending to talk about the end of this thing yet, unfortunately. I don't know when this thing's ever going to end. But the current plan is next semester's online. And we'll see. I mean, we'll see what ends up happening. It sounds like it'll be online, probably for sure. And then next fall will be the big question mark. New objective week, that's right. Me and my homies hate COVID. Yeah, no kidding. Lockdowns are... I mean, we're already past the point where it got really old. But, you know... Lockdowns are the reality right now. What's up, Kirito Kataki? Online courses aren't enjoyable. Yeah, it's definitely takes away the atmosphere of the course. I think on Twitch, I think we built a decent atmosphere. I think we have like a little bit of community and even more community building than we do live, but it doesn't fully make up for the lack of in-person instruction and just seeing each other and seeing your classmates. It doesn't make up for that. And it's just tough to work from home. I know so many students just not giving it the effort they would normally do when we're IRL. Yeah, 220 and 250 online. Good luck. Oh yeah. And like last semester, it wasn't too bad being just half of the semester. Plus, we already established the courses, so we just had to continue that online. Even then, we lost quite a few students. But being online the whole semester, there's nothing real to anchor it to. At least last semester, we could anchor it to those live lectures, and we saw each other. We know we're real people and not just, people on the other side of the internet. This semester, it's tougher. But we all got to do it. I mean, we all just got to plow through and get it done. And, you'll have 220, 250 online, it looks like. And then for your 300 level courses, hopefully we'll be in person and we can get back to whatever normal is going to be in the future. I love online lectures. Hey, that's good. And to be clear, I don't mind it so much. It's just, it's tough when it's like at this point of the semester, when it's all online. In the future, I wouldn't mind doing some hybrid stuff where like most of the lectures are online, but we still get to see each other face to face and have that in person. Maybe one lecture a week is in person or something like that. But just purely online, it's wearing people down. What's up, P? Yo, you be hacking. It was nice to see some familiar names in the chat, and you be hacking. What's up, JS? Mango Mutiny. Bite. What's going on? Xenotry. Alright. The graphics of Jesse look real. No Uncanny Valley here, babies. What's up, Lipso? Lips, yo. Mundane Madman. Okay. Oh, it was... Yeah, the hackathon was 10:24. I didn't even realize that. Nice. False Tomorrow, what's up? Free lecture. Alright, so let's get started. We're at 151. Let's do this thing. So we're starting a new learning objective today. Just a recap of where we've been. I want to quickly go over the course and remind people what learning objectives are for the people who are listening. I won't spend too much time on this because, as always, the people who really need to hear a recap of what learning objectives are, let's face it, they're not listening. They're not listening. Yeah, Red Alert, the project was awesome in the hackathon. I got to judge them. They were one of the projects I got to look at, and I was just blown away when I saw it. It was awesome project. Anyway, so I'll keep this brief. But the learning objectives, you do have to pass all 5 learning objectives to pass the class. There are 3 bullet points per learning objective, so 15 bullet points that you have to get checked off in order to pass the class. Then for each learning objective, I'll verify that everything's legit by checking off that 4th box, which is just my verify. For most of you, you won't have to do anything for the verify box. I'll just check everything's legit, and I'll check it off. But if there is something fishy, I just reserve the right to override anything and say, look, I know you got credit for this, but I need you to interview with me and really prove that you complete this. The point of having a grading structure like this, the whole core of this design, is that you focus on completing these 15 bullet points. All 15 of these bullet points are actions that you can take, things that you can do. So I want you to focus on being able to do these 15 things. If you can do these 15 things, you should pass the class. And you should focus on just learning how to do those things and working on your skills to be able to do them. It's my job and the TA's jobs to identify that you have completed these bullet points and give you credit for that. You shouldn't be worried about how we're going to assess these. You should be worried about actually doing these. So if you don't have credit for one of these bullet points, especially the earlier ones, I want you to ask yourself, be really honest with yourself, read the sentence and say, can I do that? If you can't honestly look inside yourself and know in your heart that you can do that, if you don't know that, there's a reason why you didn't get credit for that. It's because the TAs and I rightfully, saw that you can actually do that. So you might be going through the motions, you might be doing interviews and stuff, but if you didn't get credit for that, just read this. If you didn't get credit for program execution interview yet, read this sentence and tell me, can you explain how a stack frame is important in the programs we write? And same with pass by reference unit testing classes and objects. If you can't do that and you don't have every part of this, really done and really know that you have that done, then our job in grading is to not give you credit for that. If you do have that done, it's our job to give you credit for that. So if you absolutely know that you can do these 3 things, it's our job to make sure you get credit for that and get credit for the learning objective. So we have students just kind of going through the motions and retaking makeup labs, retaking makeup interviews without actually knowing these bullet points, without being able to do these. And for some of them, it's very clear that they can't, and they're frustrated because they're not getting credit yet. Study these bullet points. Like, these bullet points are the core of how you're going to pass this class, so make sure you can do those things. If you can't, study. And study the concepts and the concepts behind the content, behind the concepts behind the content on what we're assessing here. Nowhere in here do we say, actually that's not the best thing, because we do, nowhere in here do we say you can do lecture questions 1 through 6. That is one thing that we use to assess your ability to write, ability to do this, but it's not the only thing. And you can get this checked off without doing lecture questions, as some students have done, by impressing us on the homework assignments. But if you can't do these, you shouldn't be getting credit for them. I did some LO1 makeup interviews a few weeks ago, and students wouldn't pass, and I would share my screen and highlight this line or read this line to them. I don't think I shared my screen, but I'd read this line to them and say, you can't, you knew exactly what I was going to ask, and you can't do that. So make sure you're studying these 15 bullet points. That's the focus of the course. Be able to do these things. And then not worry about the grading. I know this has the kind of a counter effect of some students, since the grading and assessment isn't crystal clear on how you're completing these. Some students panic. If you're used to a points-based system and a percentage-based system, I would like to reduce the panic, but I don't have, the best I can do is just explain it like this. And just focus on these bullet points. If you complete these bullet points and can do these things, my job is to give you credit for that. So don't worry about when your makeup opportunities are coming, etc. Just make sure you can do these 15 things. And then I'll make sure you pass the class. I'll give you those opportunities. I'll reach out to you and say, look, I see you're progressing through the course, but you haven't gotten credit for this bullet point yet. Let's chat. Let's interview. Let's maybe it's a reading thing. Hey, let's have a Zoom meeting and talk about why you haven't gotten credit for this yet, and we'll work it out. Anyway, with that, So we've come from program execution, where we talked about like how programs actually run in your code. Our big focus was the stack and heap memory in this learning objective. And also we introduced unit testing, classes and objects, which are kind of object-oriented programming related. But we introduced some concepts, and we also talked about Scala in general, including a lead-in week where we talk about Scala. We transitioned to object-oriented programming and functional programming, which are two paradigms that allow you to approach a problem in different ways. Each of these have certain advantages and disadvantages, and for each of these, I restricted what you can do specifically to force you to use one approach or the other. So I banned control flow to force you into object-oriented programming, and I banned var to force you into functional programming. And hopefully you've kind of experienced how different these two paradigms are. And then moving forward, I'm not going to ban anything anymore. We're going to start data structures and algorithms today. I'm not banning anything anymore because I don't have to force you to use data structures and algorithms. It's going to be up to you to decide if you want to use an object-oriented approach, a functional approach, or you don't want to use either of those and you want to use like a 115 approach. It's up to you to start deciding which approach is going to be the best for the current situation, the current homework, the current lecture question. It's up to you to decide that moving forward. I'll use a mix of both in lectures. So we'll have state changing in our objects. We'll also see some recursion. We'll see some first-order functions. I'm going to use a lot of tools from both paradigms. So we're going to start seeing a mix of those moving forward. And again, it's up to you on your code what paradigms you're going to use. And then, and to this end, we're going to talk about linked lists, trees, and graphs with 2 lectures on each. Linked lists start today. And then the last 2 weeks for learning objectives is event-based architectures, where we're going to explore what happens when you have 2 pieces of code running effectively at the same time. They don't, technically they don't run exactly at the same time, but effectively at the same time. Actually, I take that back. I think sometimes it does, the way we're going to set this up. When you have 2 pieces of code working at the same time, and they're going to communicate to each other by passing messages to each other. And we're going to do that using an actor system in Scala and also WebSockets to enhance our web apps to be real-time and have users be able to communicate in real time and interact with each other in real time. And one of the key points, one thing I didn't emphasize as much as I wanted to during functional programming, the idea of immutability. We say when we pass a reference to an object, we know that the method that we call can't mutate our object. It can't change any of the values and the state variables. And that's one of the advantages to immutability, is that even when we're using pass by reference, we don't have to worry about our objects changing state when we give a reference and share a reference across our code. This is even more important when we're talking about concurrency and different pieces of code running at the same time, which is concurrency. If we're sharing data and we're using that data at the same time, not even just a method call in another stack frame, but we're using that data at the same time and it's changing, this is going to introduce really wild and very difficult to debug bugs if one of those pieces of code is modifying that data while another piece of code is reading that data. So when we're talking about event-based architectures, message passing, and concurrency in general, it's very important that the data is not changing. And if we use immutable types and immutable objects, then we don't have to worry about that at all. We can share immutable objects across this code, and there's no concern about the state changing as you're using an object, which is much scarier than as you're calling a method and waiting for it to return it changed state. If it's changing state, think of a list, a mutable list. If you're iterating over it and it's changing state, some other code is changing its state and adding elements or changing values as you're in the middle of looping over that data. Think about how much that can break things and how hard that can be to find that bug. It's going to be a very tough one to debug. So that's kind of the high structure of the course. That's basically everything that is 116 right now in a nutshell. And then we'll have 1 week of pulling it all together. This MMO architecture, I'll pull all the concepts together and build a large application using all these concepts, then a week of review. So with that, a little bit more of a lead-in, 10 minutes than I quite wanted to do, but hopefully at least someone got benefit out of it. This week's LO3 interview, that's right. With UB Hacking, it was we got the interview assignments out a little bit later than we normally do, but you should be getting your email soon. We made the list last night, so it might be a little while. It might probably be today that you get your emails. If it's a little later than normal, don't panic yet. You'll get it. All right, so with that, let's dive into some data structures and algorithms. We're going to talk about data structures and algorithms today with linked list. All right, so our lecture question today, we're going to build a linked list today. It's in the repo, but we're going to explain what it does and how it does it through this linked list node class. Your lecture question is going to be to add to this class and add an algorithm to this class, which is the reduce function, the reduce method that we saw a week from today, last Monday's lecture. Reduce was one of the methods that we looked at. So this is going to take a function of the type parameter, of two values of the type parameter, and return one. So we're going to reduce this entire list into a single value using this function and return that single value. You can assume that the function provided is commutative. So f of ab is the same as f of ba. Like addition down here, it's commutative. A plus b is the same as b plus a. If the list is size 1, just return the value without applying the function at all. And you can assume that you don't have the empty list, that won't be an input, which will make a little more sense when we talk about the structure of this linked list node class, that we can't really have an empty list. The way we're going to represent it, we can't have an empty list. It's one of the restrictions, but I'm using it to teach you the concept of linked lists, and not to actually use this out in production. So we're okay with that. And then a test suite, test reduce, which is going to test the functionality above. And I want you to use different type parameters. Like I have an example with ints here. You should use at least 2 different type parameters in your testing. And don't test with the empty list because we can't handle that. Time to do linked lists in C. Yeah, you can. It might even be easier in C, to be honest, when you just do it as a struct. But you'll do that next semester in 220, so as Dennis Grace points out. So a quick recap of what we know about arrays and lists at this point. So arrays are sequential, and they're one continuous block of memory. So we can access any element in an array very easily and very efficiently with this random access. So the idea here is that we have a reference to the first element of an array. So we have that address to the first element, the actual memory address. And if we want to access element I, or the element at some index, we're going to multiply that index by the size of each element in bytes, and then add that to the first address, and that's going to give us exactly the memory address of the value that we're looking for, the value at that index. So we can jump to any spot in memory. It doesn't take us any extra, barely any extra effort, constant effort. So in Big O, we don't care about it at all. It's one multiplication, one addition, and then a memory lookup in RAM. That's all it takes to get any element of an array. So that's why we access arrays at some index. We say, give me the value at index 20, and that doesn't take any time. That's an O of 1 operation, very quick. More details to come in 250. I'll explore this in great depth. But we can get any value at any index very efficiently. The downside of this is its fixed size. We can't grow an array since it has to be sequential. We don't know if the next address for the next element that we would want to add would actually be available to us. So on the heap, we have some array at address. Oh, I forgot my at symbols. At some memory address, we'll say 1503 here, and that's where the first element is. And then the next element, depending on the type that's stored in this array, however much memory that type takes up. So say this is a double, it's going to take 64 bits. So we move down 8 bytes. 8 bytes in memory, that's going to be where the next one is. 8 more bytes in memory, jump up 8 more bytes, that's going to be the next value. 8 more bytes, that's the next value. Let's say this is an array of size 4, and the next part of the heap space, that next memory address, 8 bytes ahead of this last value might not be available to us. We're in the heap. When we build an array, we always have to specify its size. And we got an array of size 4 allocated to us in the heap space. And that next memory address might be used by another program. It might be used by another object in our own program. In general, it's just not available to us. So we can't expand this into an array of size 5. Just not something we're allowed to do. Arrays have to be fixed size, and the size has to be specified at creation. There are some ways to kind of simulate getting around this. If you've used a language that you've used arrays that can change size, what that language is doing behind the scenes is when you want to add to the end of it, it'll actually create an array with a larger size, copy all the elements over into the new array, and then return a reference to the new array, but it does it all behind the scenes, so you don't actually see that happening. And then it'll ask for more memory than it needs, so it can expand sometimes without even copying over. Again, 250 will explain all the details there. Yeah, just like C arrays. So C arrays will expose this to you. C won't hide any details at all. You're going to see all the details in a C array. You're gonna, but all languages, arrays in every language behave like this. But a lot of languages will hide the details. I don't really show arrays in Scala, but Scala arrays do the same thing. Java arrays do the same thing too, but we usually use array list, which hides all the details from us and hides all the resizing and everything. There's the daily, yeah. And there is some content overlap on purpose between 116 and 191. If I mention 191 material, it's just going to reinforce it for both classes. All right, so that's arrays. Let's put that behind us. You'll talk about arrays again in 250. I intentionally don't really talk about them much in this class, so we can focus on linked lists. Linked lists are also sequential, except instead of being one continuous block of memory, they're spread across memory. They're all over the place. We have no idea where each value is for a linked list, and we can't easily just access the element at some index. There's no sense of indices in linked list. We pretend there are by calling the apply method, but it's not doing the same thing as an array where it's accessing the element at that index, and we'll see the details of how that works in a little bit. But each element does know where to find the next element, and that's all it knows. So each element of a linked list, node as we'll call them, knows its value that it's storing and where to find the next node, which stores the next value. And that's it. That's what a linked list is in its essence. The advantage of this is its variable size. So since each element just points to the next element, we can create a new element and update our list to point to that new element and expand the size of the list. Since that new element can be anywhere in heap space, we can expand this list just by asking for more heap space. Hey OS, hey JVM, give me heap space for another linked list node. I'm going to expand my list. It says, okay, here you go. Here's the memory address of that new memory that I gave you. And then you can work with that memory address and expand your list. And that looks like this. Oh, I forgot my @ symbols here too. I should have updated this slide. So here's a list containing the elements 5, 3, and 1. On the stack, when we have a reference to our list on the stack, that's only a reference to the first node in the list. So on the stack, say we have some variable myList with a value that refers to the first node on the heap. That node knows the value that it stores, 5 in this case, the first element of the list, and a reference to the next element, the next node of the list. We follow that reference, we find the next value 3, and a reference to the next node in the list. That reference is going to show us where in heap space we can find the next value, which is 1, and also a reference to the next node in the list. And here we're going to use something called null termination. We're going to say that this linked list is null terminated because once we read a null character, we're going to know that that's the termination of that list. This is the end of the list. So once we read an element, oh my god, Java. I don't know if y'all could see that. Java wants to update. I'll save my rant. So when the next element is null, we're going to say this is null terminated. So that's the end of the list. We're going to say if the next value is null, that's it. I'll give a quick side story on this, a quick note, and then we'll just take it as fact from here on out. But null, the use of the keyword null is discouraged by the Scala community. The only reason I'm using it here, or one of the reasons I should say I'm using it here, is because in 220 using C, you are going to see null termination. So I want you to get used to this idea of using null, and specifically your character arrays are going to be null terminated. So there's no string in C. You have to use an array of characters, and C will let you read off of the edge of an array. So you need some way to determine, some way to signify that this is the end of the string or the end of the array. And we do that by adding a null character to the end. So once you read null, you know you've reached the end of that character sequence or character array, and that's the end of your simulated string in C. Since you're going to see that in detail in C in 220, I want to get you used to seeing null, even though the Scala community discourages that. It is part of the language still, though, so we can still use it. So let's break that down into some code. So a linked list is built with a linked list node, and this is it. In its purest, rawest form, this is a linked list. It's a class. It's going to take some type parameter, because we can have linked lists of any type. In Scala, you can create a Scala list of ints, a list of doubles, a list of animals, a list of dynamic objects, etc. You can put any type parameter. So we better have a type parameter. We don't want a linked list that can only store one type. So we're going to take a type parameter, store a value of that type parameter, which is the value this node of the list stores, and a reference to the next linked list node of that same type, which might be null in some cases if it's the last element of that list. Dennis Grace, if you missed that, you'll be happy with 220. You're going to see null pointer exception and I forgot the other one, but the error that you always see in C a lot in 220. Oh, that's bugging me. What's the... it's bugging me. But there's another error you're going to see a lot in C. So to create this list, we're going to create a new node containing an element of the list, 1 in this case, and the next node is going to be null. We don't have any other node to refer to, so we're just going to say null. My goodness, Windows, shut up. It's going to refer to null because we only have one node at this point, and we're going to refer to null to say this is the end of the list. Then we're going to reassign that list a new list containing the element that we have already and the element 3 prepended to it. So usually you don't see the details of this when we just say we use the : operator, but this would be the prepend operator. Yeah, you have to, and we're going to explain that. We're going to talk about that a lot in the next 2 days. A lot of it today, actually. So we're going to build this backwards. We're going to create, as Byte points out, and we're going to create the next element, 3. And the highlight of that is going to be why, I've mentioned this throughout the semester, why appending to a list is a very expensive operation, but prepending to a list is very cheap. And this is why. It's because we can naturally build these linked lists backwards, but building them forward and appending to the end of a list is a very expensive operation, especially when it's immutable. It's a very expensive operation. So we're going to create a new linked list node, storing the value 3. And then the next node is going to be the value that my list was storing, which is this first linked list node that we created. So now we have a list containing the element 3 as the first element, refers to my list, which at the time stored this linked list node of 1, and then the next node is null. So we have no list. That's the end of the list. Then we're going to reassign my list again to a new linked list node with the value 5, and referring to my list, which at this point in time refers to this node containing the value 3. So now our final list is 353, or 351. The linked list node that we're going to build in this class is mutable. So just for what it's worth, it is mutable. But don't worry, in 250, you're going to see immutable lists. You're going to see immutable trees, which is a fascinating topic. A lot of complex stuff going on, a lot of fun stuff. But today, in this class, we're going to build a mutable linked list. And for what it's worth, it's going to be a singly linked list. In 250, you're also going to see a doubly linked list, which means you have a reference to each node has a reference to the next and previous node in the list. For 116, singly linked list only, and they're going to be mutable. All right, so let's go through this line by line and see what's happening on the stack and heap as we execute this program and as we build this list. So we're going to create a new linked list node with the value 1 referring to null. So this value 1 next is null, which is a keyword in Scala. This is null just represents nothing in programming. You may not have seen this in 115 in JavaScript or Python, but null just means nothing. There's no value. It's really nothing really exists with it. So we use null just as a placeholder to say nothing, no value, nothing is here. So we'll create this linked list node, value 1, next is null, and we'll say that it's at 416 is its reference number. Assign that to my list. My list refers to 416 to this linked list node, and our list is effectively size 1. The next line, we're going to create another new linked list node with the value 3, and next is going to be my list. And at the time, so whenever we have an assignment, the right-hand side is always evaluated before the left-hand side. So at the time, the right-hand side, my list, was storing the reference at 416. So the value for this new linked list node is the next value is going to be at 416. It's going to refer to the previous node that we created because that's what was in my list. And then we're going to assign my list equal to the reference returned by this constructor call, which we're going to say, again, these references, the numbers are just made up just to show that these can be anywhere in the heap. But this reference at 795, that's what's going to be stored in my list after this line is executed. And then we'll, so now we have a list effectively of length 2. And notice that my list is always storing a reference to the first node of the list. Now this node refers to another node, so we effectively have a list of length 3, or sorry, a list of length 2, but we're referring to just a single node, just through my list, without writing any algorithm. So with our current linked list node, we have no way of knowing the size of this list. For example, something we tend to take for granted. We can just ask a list for its size, and we'll build the size method today. But just through this reference, we only can access the first node of the list directly, and then we have to access next to get to the rest of the list, and keep accessing next until we read null, and then we finally know the entire list, and we can start thinking about what what this list represents, what the values are, etc. So we run the last line. We're going to create another new node with value 5. And next is going to refer to whatever my list was storing before this line was called, which was at 795. So this node is going to refer to at 795 as its second parameter. It's next 795, and then return wherever the JVM ended up giving us heap space. Just arbitrarily, I'm going to pick 506 for the slide. Give us some reference, and now my list is storing that reference to at 506, which is the new head of this linked list, the first element of this linked list. So now our linked list effectively has value size 3, but we're still just storing a reference to a single node, a single linked list node. So we refer to 506, which refers to 795, which refers to 416, which refers to null. So we can traverse this list, but not directly. There's no way we can just do some math and go from this reference to this reference. We can't do that. We have to follow the chain. We have to follow the links to be able to gain information about the entire list. If you printed out my list, would it print out the reference? Yeah, it would print out at 50. It would print out linked list node at 506 is what this would print out, because we don't have any toString method yet. So the Scala list has a toString method, and we'll build a toString method as well that iterates, that traverses the entire list and calls toString on each element as it traverses the list. We don't have that yet. If this is our entire linked list node, it's just going to print out the reference. Same with equality. It's just going to compare by reference. So let's let this settle for a second, because this is a linked list. Like this is it. Everything else that we talk about linked lists are either going to be applications and implications of this, or algorithms that we're going to add. And the rest of today's lecture is algorithms that we're going to add to this. So we don't have much functionality here. So we're going to write methods that will traverse this list and give us useful information, like the size of the list is the first one we'll talk about. Is LQ confusing, or am I dumb? I can't attest to the second part of that, but it should be confusing now unless you've read ahead in the slides and watched the lecture. That lecture question isn't going to make sense until we see the algorithms, because you just learned what a linked list is. And if you were looking at the lecture question while I was explaining what a linked list is, it's just going to make it tougher. So that would be why it wouldn't make sense. That isn't a lecture question that you can just kind of jump into without paying attention to. I'd argue that all lecture questions are like that. You can't just jump in without watching the lecture. Yet many students try to do that, and I don't know what to do about that. I already told you how to do these in lecture. Just watch the lecture. All right, but yeah, the lecture question shouldn't make sense yet. I haven't gotten to the end of the lecture. Okay, so let's keep going. So let's look at how to do these things. Like, that's great, structure of a linked list. That is the fundamental, that is what a linked list is what we just talked about. But we can't do anything with that, so let's start doing things with it. So let's look at algorithms to do these 5 things. Find the size of the list, print all the elements of the list, access an element by its location, add and remove elements, I guess 6 things because that's 2 right there, and then find a specific value in the list. So size, and I'm going to show these as recursive methods. So to find the size of a list, we have to traverse the entire list. There's no other way for us to find the size, because we have to traverse the entire list until we find a null. Before we find a null, we have no idea. There could be a million more elements, or there could be one more element. Until we reach a null, we cannot determine its size. So we do have to iterate over the entire list, making this an O of n runtime algorithm. Most algorithms that we see are going to be O of n, quite possibly all. I think all of them are going to be O of n with a list, except prepend. It's going to be O of 1. So we're going to do this recursively. Our base case, if next is null, we're at the end of the list. And all these methods, by the way, are going to be added to the linked list node class. And if you check out the examples repo, all of those are there already. All these methods we're going to cover are there, and you can play with them. So if next is null, I have a list of size 1. I'm going to return 1. Easy enough. The base case should always be some simple input-output. A linked list node where next is null, that's a list of size 1, return it. Return 1. Done. If the size is not 1, then we're going to call this .next.size. So say this is a list of size, a linked list node that has 4 more elements after it. So a list representing a list of size 5. I'm going to call .next is size. That should return 4 if everything's working right. I'm going to assume that that's correct, and it's going to return 4. And I'm going to add 1 to it to get my total list of 5. So whatever this .next.size is, should be 1 minus the length of this list minus 1. So I'm going to add 1 to it to say, whatever that guy says, plus 1 for me, and then return that to whoever called .size. in toString, if we want to print out all the elements of a list, we're going to override the toString method to be able to get all these values in one string in the way that we're used to seeing them, and then print it out. So if the list has only one element, if next is null, I have a list of size 1, access its value, call its toString, and return that. Just one element, toString, done. Otherwise, I'm going to still toString the value that I'm looking at and append to it a comma separating the values and this.next.toString. So whatever this.next.toString, the next node in this list, its toString should return a string representing all of the elements from that element onward. And I'm going to prepend to that string a comma and the value that I'm looking at, and then return that up the recursion. And I want to, just to make sure those points are clear, I want to jump to the debugger. Week 8, which is actually week 9 this year, if you can believe that. Week 9 already. So here's our linked list node. So you know what? I did do that. I don't know why I didn't have this one in the. I noticed that before lecture, and I forgot to add the old one. One. Next size. So let me just get it looking like it does in the slides. Size and toString. And let's go to our linked list example, and I want to print line mylist.size. Go back up to size, set a breakpoint, and I want to run this and see what's happening in that list. If for those of you who are still getting used to the debugger, I'm going to set this breakpoint. I'm going to set that breakpoint, which is going to, when I run in debug mode, run my program until it hits this breakpoint for the first time. So just like your labs where I have a highlighted line and I say, what's the state of the program at this highlighted line? Those are, I'm simulating breakpoints there. I'm saying if a breakpoint was here and you ran the program in the debugger, what would the debugger tell you about the program at that point in time? So let's run this in debug mode. Wait for it to compile. Get an error from, oh my goodness. From the last lecture. Just comment a bunch of that out. Run this in debugger. Seriously, one of my favorite things to do in office hours when students are having a problem, I'll just say, run it in the debugger and tell me what the debugger says. And most of the time they'll be like, what's a debugger? And then I get to teach them about debuggers. And then their mistakes just jump right out at them. The debugger is basically like, here's your mistake, here's what's going on. So here in size, first of all, this is in the debugger. This is going to call toString on the method and show you what its toString returns. And we can see the result of our toString call, 531. And we can break this apart. It's referring to a linked list node at 855 that has an integer 5 and also a linked list node at 593 or 559. That has a value of 3 and refers to at 862. That has a value of 1 and refers to null. So we can see all the links in our linked list. And one thing to notice about linked lists is this linked list node is representing this list 531. But if we had a reference just to its next, if we grab this reference and store that in a variable, this is exactly a list with the elements 31. And it doesn't know, nor does it care that it's being referred to by this linked list node containing the value 5. These are completely separate lists. but we can chain them together, or dare I say link them together, to be able to create a full list of values like this. So I'm going to take my debugger and I'm going to step, and next this dot next is not null. It's this list with 3 1. So we're going to call dot next dot size plus 1. 3 1 not next is not null. And then when we get to the list of just 1, when we get to that recursive call, and we can see our whole stack, all the stacks on the frames on the stack. When we get to this call, we reach our base case, return 1. We go return that to this stack frame, which is waiting for next.size. So when we return that, next.size is going to return 1. We're going to add 1 to that. We're going to add 1 to that and return 3. We get the return 2, return that, which is going to be 3. And then finally, in our main program, we're going to print out 3 to the console. So we're recursively calling Did I exit full screen? Why did I do that? Or did Windows do that for me? So we're recursively calling this, and as we get the recursive calls back up, as the stack frames start returning from the base case, each time we get a return value, we're going to add 1 to it and then return that. Add 1, return that. Add 1, return that. Similar to the toString, I'm not going to show that in the debugger in the interest of time, but we hit the last element. We're going to convert its value to a string and return that. Prepend this value, return that. That's what's returned here. Prepend a value, return it. Prepend a value, return it, all the way up the recursion as these stack frames are returning. And then we're going to accumulate this whole string containing all of the values in that linked list. In the debugger, when it said 3.1, it was calling my toString method. So my toString method was going through all the recursion to the end of the list and then coming back up and then telling the debugger, hey, if you want to show the human that's using you what I'm supposed to look like, I did all this recursion and it returned 3.1. So can you show that to the human? That'd be super duper. And then we get to look at that call of the toString method. It happened to be an O of n call to toString that the debugger made to be able to show that to us, but it is using my toString. Maybe that's worth just very quickly showing. So if I take my toString and I rerun the debugger, we'll only get the references. We won't get that nice showing. So now it's just saying at reference, at reference, at reference, because I don't have my toString anymore. So it doesn't know how to tell me what these things are. So it's just going to give me the default toString, which is type at reference, type at reference, type at reference, null. All right, so let's rip through a couple more algorithms. How accessing an element at the list using apply. This is how we say, I want the 4th element in this linked list. We call the apply method. If you're wondering why it's not just like an array access, even though you can use parenthesis notation on a linked list and get access an element like that, why we use this apply method, why I don't show the parenthesis notation, but I did for arrays when we very briefly, very early on covered it. Is because this is not accessing an index. It's simulating accessing an index by calling next, accessing next that many times. So if I do apply of 4, that's the same thing as saying this dot next dot next dot next dot next is the same exact thing, and that's how it works in the Scala list as well. So this is an O of n runtime operation because it has to traverse to get an element in the list by index. It has to traverse the list that many times to get to that element. There's no other way of knowing where that value is in heap space except by following the references and following the links. So if our recursive algorithm to do that, if I equals 0, we're basically saying access this element, so just return it. And return the entire node. We're going to assume that we don't want to get the value. We're going to return the entire node, and then the caller can say .value if it wants the actual value at this at that location. Otherwise, this .next, so we're going to call next one time, and then tell that node, hey, you have to call next I-1 times. So we're getting closer to our base case. Our logic is sound. If I need to call next 4 times, I'm going to call next once and then say, hey, next node, call next 3 times. And my base case, if I shouldn't call next any times, just return it. So this is why apply, when we're covering sorting algorithms, and I said I'm using apply inside a nested loop, so I'm actually n cubed here. This is why, because apply has to go through the entire list to be able to access that element. The apply method is very slow. To avoid that, we'd have to use iterators, which I didn't talk about this semester, but it's in the repo. Or we can get smarter about just how we access elements without iterators, which I did this semester, to get rid of that apply. I think I used recursion to do it without needing apply this semester. Yeah, I did recursion and dropped elements at the beginning of the list. That's how I got around it this semester, to get a faster sort. All right, adding an element. To add an element, we're going to need access to the node right before the location where we want to add. So assume we have this list, and this is how I'm going to draw a linked list from now on. I'm going to drop the ats and everything and use arrows like this. So this means next is referring to this node, this next is referring to this node, this next is referring to null, and we have the end of the list. Say we want to add the value 2 right after 3. So in between 3 and 1, I want to add the value 2. First, I'm going to need a reference to this node, and then from this node, I'm going to call the add method. So assume we have a reference to this node. I'm going to call .add on this node, and that's going to add that element right after this while maintaining the rest of the list. So to do that, we're going to take this node, remember temporarily what its next referred to, because next was referring to this node. We don't know anything about that node, but we know we need to preserve the reference to it. Then this next is going to be refer to a new node that we create with the element we want to add, and the next value of that node that we created has to refer to whatever the next value of this node was referring to. So it's kind of a mouthful. That's why I like the picture for this one. We add that element, we create a new element, and make sure the next values refer to the nodes that they need to be referring to be able to create this new linked list. In code, that's going to look like this. If we're at, remember this is called on a linked list node, so this would be called from that node containing 3. We're going to create a new linked list node that has the element we're adding, refers to whatever we used to be referring to, and then update this .next to that new linked list that we created. And we can conveniently get this done in just one line here. To delete a node, we're going to need a reference. Similarly, we're going to need a reference to the node right before the node we're going to delete, because we have to update its next. We can't just delete this node without thinking about the previous node, because this node has to update its next value to get rid of that node. And delete is actually simpler than add. If you can believe that, we did that in one line. In the code, it's simpler. Conceptually, both of these might take a little time to think about. But in the code, at least, we need to update the node's next to the node we're deleting's next. So whatever the value this node that we're deleting refers to, this node is now going to refer to that node. Now, this node that we technically deleted from the list still exists, and it even still refers to the node that it was referring to. Everything here is intact still. But since nothing refers to it, it's effectively deleted. And in fact, as long as no other parts of our code will be using this node, it's going to get garbage collected and destroyed. It's going to be removed from the heap. So it still exists, but it will get swept up. When you're coding in C in 220, you would have to clean this up. You'd have to free up that memory yourself. We're in Scala with garbage collection, so we're not going to sweat it too much. And in the code, this.next equals this.next.next. For what it's worth, if we call delete after on the last element of the list, this will crash. This will be a null pointer exception. So there are limitations to the linked list that we're creating in class. And I'm going to overlook those because you'll talk all about things like that in 250. We need to keep this as simple as we can with still covering the concept. And yeah, that node, not referred to anymore. It's just forgotten. It's sad, I know, but yeah, we just cut that node out, and that's how we do it. This.next, that's the node that we're removing. Whatever node it was referring to, that's the node we're now referring to in this node that we're calling delete after. And our last algorithm we'll talk about, oh my goodness, we're 3 minutes over already. The last algorithm today, luckily it's the last one, is, actually there is one more, but I won't be able to cover it today. We're going to find a specific value. So we get a value of type A, and we need to find this in the list, and then return a node to that reference, or a reference to that node containing that element. In fact, we're going to find the first occurrence of this element. If it's duplicated in this list, we're going to return a reference to the first node in the list containing that element. And notice that we are returning linked list nodes in these algorithms. And for adding and deleting, we needed a reference to that node that from the one before we wanted to add or delete. So if we're returning references to our nodes, we can call methods on these nodes. So maybe we want to find a node with a particular value and then add an element after that value. We would call find, that returns the node, and then call add on that node that's returned. So we can chain these things together and work with the references to nodes to be able to get what we want. You can chain refer, say, yeah, so .next returns a reference to a linked list node. So you can call .next on that and chain them together like that. You sure can do that. Like this .next returns a reference to a linked list node, and then we'll call .find on that node that's returned. We don't have to store this in a variable or value intermittently. We can just chain these things together. .next, .find. .find returns another node. We could do whatever, though we might want to check if that returns null first. We can chain these things together as much as we want. Yep, like the vote counter. Check out the bonus slide for vote counter from Friday's lecture. We did that quite a bit. And so to find a particular element, well, if this node contains that element based on whatever its equality dot equals method does, if they're equal, return this node. This is the node containing that value. If we're at the end of the list, return null to indicate just something to indicate that we didn't find that element. The element is not in this list. Else, if we're not at the end of the list and this node doesn't contain the value we're looking for, call find on the next element. So check the next element and keep doing that until we either find the element or reach the end of the list. I don't know if I'll end up coming back to these in the next lecture. I want to cover that stuff. I might just go over time. Hopefully you don't mind. A quick side note, you could do any of these methods iteratively. You could write a loop to do the same thing. It's up to you to decide which one you like better. Personally, I like the recursive one, but if you want to stick with loops, it's whatever. But by the time we get to trees, I'll talk about recursion versus iteration again. And I'll challenge you when it comes to trees to write those. I'll show you recursive algorithms. I challenge you to do those iteratively with loops. It's much, much more difficult than with linked lists. With linked lists, it ain't too bad. With trees, we're going to see why we studied recursion. It's going to make those tasks way easier. I'll just quickly go through these last few. For each, given a function that returns unit, call that function on each node in the list. So if I'm calling this on a node, I'm going to call the function on its value, and then as long as we're not at the end of the list, call for each on the next node. So each node is going to call that function on its value, and then send it down the list. Hey, you, call this on your value. And then that node's going to say, hey, you, next node, call this on your value till we reach the end of the list. Map. So recall when we saw map in Scala, we had a list. We want to create a new list with some function applied to it. We used it to square each number in a list. So we squared all the numbers in this list by giving it a calling map and giving it a function that squared numbers. And then that created a brand new list with all the numbers squared. So we want to do the same thing with our linked list. We're going to take some function. We're going to apply that function to the value we're looking at. And if we're at the end of the list, that's our base case of our recursion, we're going to return a new linked list node with the new value with that function applied and referring to null. If we're not at the end of the list, we're going to call this.next.map of f. So the next element, call map, assume that our map method works. That's going to return a list with all of the rest of the values in the list with that function applied. And then we want to create a new node with this value for this node prepended to the beginning of that new list and then return that. So we have all the ingredients for successful recursion. And we're going to call map on, we call map on the head of a linked list, the first element. It's going to call that function on all the lists, all the nodes, values, return those back up the recursion, and prepend all of the resulting values back up and create a brand new list with all the values, all the return values of this function applied to each element of that list, like we want. And worth noting, we can actually change the type. We did this in Scala. Scala can do this, and we saw an example. If we want to do it in our programs, all we need to do is, I shouldn't say all we need to do. What we can do is take a second type parameter. So the type parameter A is part of the object. We create a linked list node of some type. We say new linked list node of type A, whatever that type is. When we call the map function, we'll provide a second type parameter, which is the type that we're mapping to, and then provide a function from A to B and return a linked list node of type B. And we do the same thing. All the logic is the same, except we have the type parameter B, which may or not, actually, no, it can't. Can't be inferred in this case. No, it can. Can it? Anyway, give the type parameter to each recursive call as well. If it can be inferred, we can remove it. I don't know if it can be inferred in this case. Maybe because new value is going to be of type B. Maybe. And then our lecture question, which again is reduce. Or we can use fold left to create a map object from list to map. Yeah, and we didn't do fold left or fold right, but your lecture question is to do reduce. I won't have you do fold left or fold right because it's a method that takes two parameter lists. I don't know, it's just another thing I'd have to cover. I'm always looking for those kind of extra things that I can cut from the course, at least cut from forcing you to use, even if I mention them in lecture. I'm not going to have assessment on multiple parameter lists because, geez, there's so much already. All right, so that's officially the end of lecture. And we're chatting. Okay. I'm not sure what you mean, P. We can just use fold left to create a map object from list to map. I don't know what you mean there. Create a map that maps lists to maps. I don't know. I'm not following you. Yeah, that's a lot of what we're doing here. Mothman's biggest fan. You should be good at loops coming into 1.16. I assume you're all good at loops coming into 1.16. You used them a lot in 1.15. But 1.16, a big part of the goal here is to get used to recursion. It's a slippery topic. It evades the mind very easily. But we do a lot of examples, starting with functional programming and carrying on through data structures and algorithms. We're going to see a lot of recursion. And hopefully by the end of the semester, everyone, at least everyone who passes, should at least be decent at recursion. I don't expect you to be experts at recursion by the end of 116, but you should be pretty decent at it. And then future semesters, you're going to keep getting recursion reinforced. And hopefully you'll get good at it down the line. But yeah, recursion it's just tough to see what is going on with the recursion at first. It's like there's a lot of details missing when you first see it. It's, it seems like there should be more. Like, where is this creating an entire linked list? It's just not, it's not easy to see that at first. But hopefully you all are starting to get better at it. In AutoGrader, are we uploading week 8 linked list node folder? I don't know what you mean. You're from the examples repo, you're taking that linked list node class and then adding your method to that class. And then that class has to be in your submission. So when you create a zip and upload that to AutoGrader, you have to have your week 8.linked list node class with your reduce method added to it. So you're taking the existing class and then adding to it. And then submit that to Autolab in your zip. In addition to in the test package, test reduce. Submit both of those things in your zip file. And since there's no restrictions here, for those of you who like to have one big project with all your lecture questions, you can go back to doing that. Since there are no restrictions, I'm not banning any keywords. You can go back to submitting that. So what some students do, I'm not a huge fan of it, but if you clone the entire examples repo and submit the entire examples repo, I mean, it works. It works in Autolab. What are the advantages of linked list versus list? So Scala's list is a linked list. They just don't make us type linked every time. We can just shorthand it to list. Usually in programming, when we talk about lists, we're talking about linked lists. Or sometimes doubly linked lists, or some variation thereof. Oh, that one nerd. Were you asking where the repo is? Was that the question? I hope that wasn't the question. But this is why we have that week 2 lab. So the repo is linked right here. And this is why we have that week 2 lab. So you can revisit that if you're having trouble. This welcome to lab. That's why I had you clone this repo in week 2. Because we use that repo a lot. So you've had that code since you've done this lab way back when. You've had that week 8 thing, which we're now covering week 9 because of the makeup week or catch up week. But yeah, assuming it's counterintuitive, but just assume your method already works. That's that leap of faith that by the end of 116, really right now, I expect you to just believe that on faith. Just assume that it already works and then write the rest of the recursion with that assumption and just believe. You just got to believe real hard, and then, it should work if you have the 3 ingredients. In future semesters after 116, I wouldn't expect you to fully wrap your head around what's going on, really fully understand that part of the recursion. If you really broke one down and thought about it for a long time, I'd expect you to be able to draw the stack, and in fact, I'll ask you to do that this Thursday, to draw the stack, explain each stack frame that's added and returns on the stack. I expect you to be able to walk through that, but I don't expect you to be able to look at recursion and just kind of intuit what's going on and in satisfying that assumption, explain why that assumption is true. But as long as you can draw it out, it might take you a long time, but draw out the stack and stack frames and be able to write recursive algorithms based on that assumption that it works. But yeah, the finer details and just intuitively knowing what's happening on the stack, I don't expect you to be there yet until next semester, maybe even after that. Yep. Liam, yeah. So the type parameter can be an object that's stored on the heap. So we could have each linked list node's value be a reference to an object of some type on the stack. And in fact, in the examples repo, I do that right here. I create a linked list node of equipment and store 3 different object types. So I show off polymorphism in a linked list as well. So equipment is a class, an abstract class, in fact, and then I extend that with 3 other classes, and we can create a linked list node of that type, and then call the prepend method, which I didn't cover. You go over what the map algorithm does again? I only got 2 minutes till 4:42. You have to watch last Monday's lecture. I cover map, but the very short answer is it creates a new list with a function applied to each element. Yeah, it's fine. Oh, I see what you're saying. That one nerd. You can zip up the whole repo, or if you want to just take that class or the whole week 8 class and move it to a new project, whatever works for your logistics the most. As long as that class and its test class exist in whatever zip file you submit, my graders should be able to find it and grade them.